Phase kickback is something that happens only in quantum computing. This phenomena is at the base of many algorithms that show quantum speedup, including Bernstein-Vazirani, Grover's search, and phase estimation. In this video, I'll try to show what phase kickback is, why it happens, and how to use it. If you don't know what a phase is, you can watch my previous video explaining it. The link is in the description. So let's get to it.
In order to understand phase kickback, let's quickly review our understanding of the familiar controlled X gate. We think about it as having a control qubit and a target qubit, and we expect it to not do anything to the control state and only apply the X gate on the target if the control is in state 1. If we set the control in the plus state, we get a fully entangled Bell state, as we can see from the representation of the state vector here. Let's also see this in writing. We start with the plus state on the control, and with the 0 state on the target. And this is equal to 0, 0 plus 1, 0 over square root of 2. And by applying the controlled X gate, the state of the target changes only when the control is in state 1. So we have 0, 0 plus 1, 1 over square root of 2. And this is a fully entangled state. We cannot separate the qubits, and the correlation holds in whatever base we measure. But a weird thing happens if we start with the target in the minus state. So let's see that. The control is still in the plus state. But this time, the target is in the minus state. And this is equal to 0, 0 minus 0, 1 plus 1, 0 minus 1, 1 over 2. By applying the controlled X gate, whenever we have a control in a state 1, the state of the target will change. So here and here. And I'm also going to swap these two terms just to get a nice ordering. So we get 0, 0 minus 0, 1. This term is going to go to 1, 0, so minus 1, 0. And this term is going to go to 1, 1, plus 1, 1 over 2. Now we can factor out to the right, to the left, a 0, and here a minus 1 also to the left. So this is going to be 0, 0 minus 1, and the minus 1, 0 minus 1 over 2. Now we can factor out the parentheses to the right, and this will be 0 minus 1 over square root of 2, and 0 minus 1 over square root 2. So something weird just happened. We started out with a plus on the control and the minus on the target, and we ended up with a minus on the control and the minus on the target. Now, it's exactly the opposite of what we thought it would happen. The target was left alone, and the control state got a phase. Instead of a +1, we got a -1. Let's see if this happened in practice. So let's set the target to the state minus. And to see that these are in fact both state minus, we're going to measure them in the X gate by adding a Hadamard, and we expect to get a 1 on each of them. And we get the state 1, 1, which proves that the state here is minus minus. So this is phase kickback, and this combination is the basis of Deutsch's algorithm. We can also notice that the two qubits are not entangled. The fact that the target is not entangled and has not changed its state means that we can reuse it. If we use it as an ancilla qubit, we can reuse it to turn other qubits from a plus state to a minus state, like we have in this setup. This is the principle behind the Bernstein-Vazirani algorithm. Let's try to generalize this. One way to do it is to think about the control as not one qubit, but a register. If we start with the register in a full superposition, then we can have a gate that applies the X on the target only when a condition is satisfied. For all the states that the condition is satisfied, the X is applied, and for all the states that don't satisfy the condition, the X is not applied. What we expect is that the phase is copied only to the states that satisfy the condition. Let's see that mathematically. We split the full superposition into two abstract terms. The terms of the states that don't satisfy the condition, we'll call them N, and the states that satisfy the condition, let's call them S. And then we have the target that is in the minus state. Now this is equal to N0 minus N1 plus S0 minus S1 over square root of 2. Now, for all the states that satisfy the condition, the target is flipped. We'll also do the rearrangement trick. So, by applying our gate, we'll have N0 minus N1 minus S0 plus S1 over square root of 2. And this is equal to, we factor out the N and the S to the left. We have the N state, 0 minus 1 minus S, 0 minus 1 over square root of 2. And this is equal to N minus S, and then the target left in the minus state. This is what we expected to happen. All the states that satisfy the condition will gain a phase. This is a little more difficult to show in our simulator, but I have shown it in the Grover surge explanation video. And now for the big reveal, let's ask ourselves what's so special about the minus state. The answer is that the minus state is an eigenstate of the X operator, and its corresponding eigenvalue is -1, which is exactly the phase being transmitted to the control. If we have a generic operator U with an eigenstate psi and the corresponding eigenvalue e to the I phi, we know that the eigenvalues are of unit norm, so they are of this form. And if we have a setup where U is controlled and the target is in an eigenstate, then in this case, the eigenvalue will be transmitted as a phase to the states of the control that satisfy the condition to apply U. So if you ask yourselves why we need the control to be in a superposition, is because if it's in a definite state, then the phase will be a global phase and it will not be detectable. Now let's see this in writing. We start in the plus state in the control. And with an eigenstate in the target. This is just 0 psi plus 1 psi over square root of 2. And now, whenever the control is in 1, we apply u to psi. But u applied to psi is just e to the I phi times psi. So this is equal to 0 psi plus e to the I phi u psi over square root of 2. And this is just 0 plus e to the I phi 1 over square root of 2. And the target is left in the eigenstate. Now let's show this in our simulator. To do that, we'll use this gate U1, which has eigenstates 0 and 1. And for the one eigenstate, the eigenvalue is configurable via this parameter lambda. Now let's have our setup. We want to have the eigenvalue I, which means we set lambda to pi over 2, which is 1.57. We need to set the target in the eigenstate, which is 1, and the control in the superposition. Now, our u is u1 of pi over 2. Our eigenstate is the one state. And our e to the I phi eigenvalue is I. So what we expect is that the control, which is in the state plus, goes via our control u to 0 plus I 1 over square root of 2. We can kind of see this in the state vector representation, but if we measure in the y basis, this should be 0. And it is. And if we change lambda to minus pi over 2, this should get to 1. And it does. So there you have it. Now you know how to set an arbitrary phase to any term of a superposition. That is phase kickback. Thanks for watching.